Hello Shri and Shiwei. This is my video project task 3. So just going to jump straight into it. So I've just got a student declaration acknowledgement to the teachers to start off. And a table of contents going over everything I've done so far, a basic marking guide. Right, so why have I chosen this structure? So the reason I've chosen this structure specifically is because it is a bridge that is slightly different to other rail bridges in the area. So this bridge is a bridge I used to pass on my run when I was living in the city very often. So the thing that makes this area very unique is that all the train traffic coming out of North Melbourne and Southern Cross Station go across this bridge right here. So the reason I like this bridge is because no freight traffic goes over this one, so we have a more consistent loading. So as you can see here, I've just got basic measurements that which I've got using a ruler that I have put in a photo, and then using video editing techniques, I've been able to measure photo editing techniques rather, measure the distances of this, and also using the tape measure tool in Google Maps. Right. Yep, so moving on, and I've idealized this as one member, this composite structure, as I've gone through in my introduction. Right, so I've taken each of these supports as either fixed or pinned, so depending on how you view it. So from here, I've assumed it to be continuous, and I've taken this one frame here, assuming this as one member, and we are left with our ideal structure. In this case, I've chosen pinned. So from here, we've added in our loading. So I've taken my student number, I've times it by 3.33, and I've gotten a 9.99, which in my case, apply to the top and right-hand side of the structure. And then a basic deflection profile here, showing only very minor deflection due to the thickness of the concrete beam and columns. Right, so getting straight into the calculations. Moment distribution. Now the thing that makes moment distribution unique in these calculations that we're doing is that we are taking only the top loading, unlike approximate method. So I've assumed it to be fixed, and because it's fixed, I'm using 0 for my distribution factors at FAB and FDC just to get started. So from here I've taken the I values of each of these members from our base and height, worked these out. I've then substituted them into our formula, I over L for our K factors, which I've taken about each point, and then worked it out all our distribution factors. And now I've worked out our fixed end moments. Now the fixed end moments are only between this member here, as it's the only one that receives loading. Right, so from here I've substituted in all our values, and I've including distribution FEM values and whatnot, and then I've used our new technique that Shri has taught us, the moment release method. So from there, I've done our first distribution by timesing this value to this value, and this value to this value, and etc. going across here. I've then taken 50% of this value down to here, and then brought this value down here as our moment released, and then repeated this process 5 times till we have our final values here, which are just a sum value of all of these values. Right, from these values, I've then made our bending moment diagram, which are just the values taken here at the base here and transferred over. And our maximum bending moment is just done with a basic calculation, the similar calculation that is repeated in the approximate method. Right, so the shear force diagram. So the shear force diagram is just our reactions, and then all these all the values that we've got in bending moment and shear force diagram have been checked with SkySieve to confirm their legitimacy. All is well. Moving on to the approximate method. Now, It's the approximate method. So just to give context, I've shown the original structure that we're going to be working at now. So we're back to using the original structure in supports in this case. So I've got included two diagrams from the force method that we've done earlier in the task 2. And the thing that makes this method unique is that we're going to be breaking this structure down into two components, and we're going to be calling it case 1 and case 2. So in case 1, we're doing a top load. So the top load, so we're just using load that's applied, the UDL that's applied on top. Right. Now, from here, we have chosen a standard value, which is 0.15 L. Now, the thing that makes this value so important is that we are going to end up getting reaction values about the x-axis that are different to force method. Now, the reason for this is this value here affects how we work out our x-axis reactions. Now, our y reactions are worked out in a very similar way to our force method, but our x reactions here, just our basic reactions, are worked out taking into account this value. Now, just from this early on stage, we now can see that we're going to get slightly different reactions from our force method. Now, this is going to end up having a trickle-down effect onto our bending moment diagrams and other moment calculations that we've worked out. So we've broken this down, we've worked out our reactions. Now we're going to be taking a small joint section. This joint section from here is just the 0.3 of our 0.3 of our total length. So just to confirm that on the fly, yep, 0.3 of our total length, and yes, that is all good. 0.45. Taking that, so we take 0.3 of our total length, correct, and then from there we divide that by 2 and we're breaking it down in two different sections, correct. All good. So we've just confirmed that on the calculator. So now we're finding moment about B, very simple, just a basic equation. And then now we're working out our horizontal reaction forces. Right, so what have we got new? We've got a VBA and a VCD that we're working out here as well. So just go about that, working about moment about our Z. And then working about summation of X values, and we're getting our AX and our DX values from this. From here, we're working out finding our shear force and bending moments. So these are the values that we'll end up using in our that we'll be able to use to work out our bending moment and shear force diagrams. So our V values, our shear, and our M values, our moments. So we have worked out our Vx1, and I won't go through each one, but that the method continues, and basically we end up with a variable x where between x and 3 in this case, between this member 0 and 3, that's our limitations, and this just means that we can sub in a distance and spit out a value, our moment, from any point from here to here. Right, so from here, most important, we've got our loading about the top member. Right, so this loading that we've got about the top member is only between B and C. So we've just broken that down, worked out our two remaining values, and then we're working out our local maximum bending moment. Now, similar to previous methods, we know that the maximum is assumed to be between B and C. Now, because it's a uniformly distributed load, we're going to assume this is dead center. So we've taken 15 over 2, 7.5, and sub that bad boy in. So now, the unique thing about this equation is that we can substitute other values into x and get moment about different points. Right, so we subbed in our values, and we sped out our mx local max, and then we can work out our first bending moment and shear force diagrams. Right, so we've subbed in that value that we've just worked out. subbed in our other values, and what do we see straight away? We're seeing a shear force and bending moment diagram that are very similar about our y values as our force method, but slightly different because of that that other reaction that we've made as a result of that 0.15. Right. So continuing on, and we'll further compare that in the future, we are now doing case 2, which is sideways loading. So we've got rid of the top load and we're just doing the side loading. So slightly different this time. We're putting a hinge point about the deflection profile. As you can see in the deflection program, about the center, the midway point of our top member, BC. So as you can see there, we've got a very unique looking deflection profile because of this. Right, so we're breaking that down into 2 segments. Just put a little fake line in the air here. So from this, we've got both our segments and working out EX and EY about that broken about point. Very simple, moment about A, moment about D, and we're left with 2 equations, our unknowns EX, EY, and then substituting EX and EY as A and B, I then solved these equations in 4 different simultaneous equation calculators just to compare the values and spat out both these values. And more specifically, the value of EY is 2.997. Right, so we sub in the values. Now from here we can work out our reaction forces, our AX, AY, DX, DY. Now, what can we see here that's different? We don't have an unknown, the variable that we had in our first case 1. So we're going to get values more in tuned to values that we'd be seeing on similar earlier methods done in task 2. Right. So we go through that, we move it on. Now we're working out all the values you need to make our bending moment and shear force diagrams, similar to the previous method as we've gone through before. Just for an example, this right here is just to work out load about that midway point. We've worked out our local maximum bending moment at section CD because that's the value that it has load at the midway point. So in this case, we haven't just assumed that it is at midway, rather, we've taken our mx3 equation and we've solved it for x to get our midway point. Now, we can see that this is not halfway. Now the reason for this is because we do have another member here, and loading just doesn't work in this way. So if you apply loading this way, it doesn't just apply that way. So we substitute in our value into this, and we're spat out with our answer. Right, we sub in that value. We sub that value back into our shear force. Our bending moment diagram. And then we continue on the calculations. Right, so we've got 2 more unknowns at the end. Our Vx2, our Mx2, and we just do a basic equation to work these bad boys out. And we've got a limitation between 0 and 15. So just on our top member. Right, so we substitute all our values in, and we've got our shear force diagram sideways load using the approximate method. So this is from mainly using our reactions, and we can see a very different looking bending moment diagram. Very different looking bending moment diagram to other ones we've seen in the past. And this is just because we are applying load onto the side. So that's why we can see our max bending moment here on the side. Right, all values subbed in. We then add both our cases together. So we take all the values that we've added from our shear force and bending moment diagrams and plus them together. And what can we see? And we can see all the values right here just for shear force. The next page will be for bending moment. And we can see a very similar values about our y-axis. Now, why is this? This is what we were talking about before. But for the x-axis, slightly different. And we're going to see a trickle-down effect, as talked about earlier, onto our bending moment diagrams. Right, so moving on. Very, very similar, so a very good comparison. Right, so our bending moment diagrams. Right, similar values, slightly different. As you can see here, y-axis is the same. Very crucially and importantly, our bending moments here, They are the same, but very different, slightly different here. And this is because of this trickle-down effect as I was talking about. So how would we rectify this? The way, as I've talked about in conclusions and reflections about what I've found difficult, what I like the best. So just to summarize that quickly, most interesting to me was the moment distribution method because I think it's a great blast from the past. It's a great way that we worked out distributing, well, how we distributed moment in the past. And now, of course, we use computer software programs and everything. Great for job interviews, as Shri has talked about. And the most difficult, of course, I found the approximate method in this case because it's a head scratcher and it makes you constantly go back and you got to really think about your work. But to go on to this, so what could we have done different? So using the slope deflection method back in task 2, finding this x value here, we could have found. We could find this x value here, and instead of using 0.15L, we could use the actual value there, and that there would yield a much higher value. And that higher value would equate to higher values here. And these higher values here would correlate a lot more to this. But just for example, this is a good example and an accurate representation of the approximate method. So just to go over, just a basic appendix, going through task 2. And our task 1 as well, structure photos. And here is a clear example of me holding out the ruler, which was used to compare to get our lengths for the bridge. Location, basic measurements, and the approval email. All right, thank you, Shri, and thank you, Shiwei.